Okay, for the final problem in this problem set, we have 1971 AB2, and we have this region in the first quadrant that lies below both of these curves, y equals 3x squared and y equals 3 over x. And just roughly, the area is going to look something like this. And then what we have is that this area also has to be to the left of this line, y equals k, where k is greater than 1. And you should note that when k is equal to 1, where x is equal to 1, that both functions are equal. So that's where the point of intersection is at x equals 1, y equals 3. So what's going to happen here is that we have this area under here, but we don't want the whole area. As you can see, it kind of goes off to infinity, unbounded. So we're going to set up some line x equals k that has to be to the right of x equals 1. So we're just going to draw the line k over there. And k is mobile. It can be more towards 1, it can be further away from 1. Whatever it is, it now establishes the area under a curve, which would be that particular light blue shaded area there. The further k is to the right, the more area there'll be. The further k is towards 1, the less area there'll be. All right, so what we want to do is find the area of R as a function of k. Again, this is similar to the last problem we did where we have area under two different curves, and so we're going to need to set up two different integrals. So the first area is the area under the curve y equals 3x squared. Excuse me, y equals 3x squared. And that's going to be from x equals 0 to x equals 1. And then we're going to add on to that the area under the second curve. And the limits of integration there are x equals 1 to x equals k, and the function there is 3 over x. And since 3 is a constant, we can bring that out, and we get 3 times the integral from 1 to k of 1 over x dx. Alright, we're ready to find the antiderivatives of those. And for the first, it's simply x to the third. That's 3x to the third over 3 from 0 to 1. And then 3 times the natural log of x from 1 to k. First part evaluates to 1. Since the ln of k and 1 are both greater than 0, we don't need the absolute value, and we're going to have ln of k minus ln of 1. Since ln of 1 is 0, we end up with 1 plus 3 ln of k, and that's the area as a function of k under that curve there. Now the second part says what happens when that area is 7, and that's pretty straightforward. We just let that function 1 plus 3 ln of k equals 7, and you'll see that that yields ln of k is equal to 2. So 2 is the exponent that raises e to equal k. So when the area is 7, k will be e to the second, and that's the answer to the second part. Okay, and we'll find the third part. Now then the third question asks, if the area is increasing at a constant rate of 5 units, square units per second, so we can see this is going to be a related rates problem. And we start to write down our givens. dA dt is equal to 5 units squared per second. And we're looking for the rate at which k is increasing. So we want dk dt when k is equal to 15. So somehow we need an expression that relates a to k, and that's pretty straightforward. We know that a is equal to 1 plus 3 ln k. We're going to take the derivative of both sides with respect to t. Since the derivative of ln of k is 1 over k dk dt, we can now start to plug in the values we have. We know dA dt is 5, k is equal to 15, dk dt is what we want to solve for. So we really just need to multiply both sides by 5, and we end up with dk dt is 25 units per second when k is equal to 15. Alright, so that's kind of a related rates and area problem all work together along with exponentials, etc. there. Alright, so that's the end of this.